Hello, welcome to this video. And in this video, we're looking at the applications, differentiation in velocity and acceleration. So we want to use differentiation to determine the velocity at an instant. Consider a particle whose motion is represented by the displacement time graph below that you can see. Now, as you can see, its velocity varies as shown by the curve OPQ. Now, at point P, if it were to continue at that very velocity onwards, the graph would go along PT, along that line there. And that's the velocity at P can be computed by calculating the gradient of the tangent to the curve at point P. But if the particle's displacement is a function of time, the function whose representation is given by the curve OPQ, then we can differentiate that function to get the gradient of the tangent, which we know in this case would be the velocity at any point. We want the velocity at P, so in that case, it would be the velocity at P, but we'll be able to get the velocity at any point because it will be the gradient of the tangent at any point along the curve. Now let's relate this to average velocity. Yeah, so average velocity is the ratio of the distance moved to the time taken over a particular interval. It's like saying this particle would be moving at a constant velocity from this point to this point. Now, on the graph that we have the graph S is equal to 4.9 t squared. S is the displacement, t is the time in seconds. And so from P to Q, yeah, from P to Q, the average velocity from P to Q would be the distance moved from P to Q, which is from 4.9 to 9.6 meters, delta S, the change in displacement or distance divided by the change in time. So delta S out of delta T. But what do we know? We know from differentiation that as delta T tends to 0, delta S out of delta T will tend to the gradient of the tangent at point P. But we know that the gradient of the tangent at point P is in fact the velocity at point P. And so the relationship we have is that V is equal to ds, V is equal to ds dt. And that's how we'll be getting the velocity at any instant. So the velocity at any instant is defined as the limit of the average velocity, one interval following that instant, as the interval tends to 0. In that case, we're saying that the interval here is delta t. Yeah. So the limit of the average velocity, in other words, we're defining V as the limit as delta t tends to 0 of delta S out of delta t. And this is in fact ds dt. Now, similarly, acceleration at an instant is defined as the limit of the average acceleration for an interval following that instant as the interval tends to 0. So here we're looking at the limit as delta t tends to 0 of the change in velocity, because acceleration is the rate of change of velocity, just as velocity is the rate of change of distance, of displacement. And so in this case, we'll have that acceleration is dv dt. And so we have those relationships right there, and we can use these equations to solve questions like the examples that we have in front of us. So we have that a body moves in a straight line in a distance s meters in a time t seconds, and s is given by t cubed. Find the velocity and acceleration of the body after 2 seconds. So we have that s is equal to t cubed. That's the equation of our displacement. We know that v, the velocity at any time, is given by ds dt. And so this will be, when you differentiate t cubed, you get 3t squared. And we know that the acceleration is dv dt. And so acceleration is going to be the derivative of 3t squared with respect to t, which is 6t. Therefore, after 2 seconds, v will be given by 3 times 2 squared, which is 12, and the displacement was in meters and time was in seconds, so this will be meters per second, and the acceleration will be 6 times 2, which is 12 meters per square second. So that would be our answer in that case. So it's as simple as that. Let's look at another question here. So here we've been given our s as t to the power 4 plus 3t squared. We want to get the acceleration. We know that velocity is the derivative of the displacement. And so this would be 4t cubed plus 6t. We know that acceleration is the derivative of the velocity. So this would be dv dt, which is going to be 12t squared plus 6. Now acceleration when t is 1, we could write this as a1 since it's a function of time. This is going to be 12 times 1 squared plus 6, which is simply 18 meters per square second. The acceleration when t is 2 would be 12 times 2 squared, which is 12 times 4, which is 48 plus 6. It's going to give us 54 meters per square second. And the acceleration when t is 3, we could write like that. 12 times 3 squared plus 6, which is 108 plus 6, which is 114 meters per square second. Now for part B, we've been asked to get the average acceleration between t is 1 and t is 3. Now remember, average acceleration is what? The change in velocity divided by the change in time. So temptation for you to calculate, go with, a1 plus a of 3 out of, 2. This would be wrong. Because that's not the average acceleration between those two times. Because the acceleration is not changing uniformly. And so what we have instead is we have the acceleration between, let me just write it as the average acceleration between those two times for that time interval as the velocity, the change in velocity divided by the change in time. So we have to get the velocity when t is 3. How do we get that? The velocity when t is 3, would use this expression right there, would be 4 times 3 cubed, which is 108. 108 plus 6 times 3, 108 plus 18, which is 126 meters per second. Minus the velocity when t is 1, which is 4 times 1 cubed plus 6 times 1, which is 10 meters per second. This divided by 2 seconds. And this gives us the correct answer as 58 meters per square second as the average acceleration between t is equal to 1 and t is equal to 3. So this is how we do questions like this and use differentiation in velocity and acceleration.